Okay, so pre-lab problem. So we have a meter stick. The axis, we're told in the problem that the axis is directly in the middle of the meter stick. So let's just say that like this is the 0 centimeter end. A meter stick has 100 centimeters. So over here, this would be the 100 centimeter end. So the axis is right at the 50 centimeter mark. Okay, for torque problems, distances are important. Okay, now these types of problems start out with a free body diagram. We're essentially looking at the forces that are acting on the meter stick. So this meter stick has 4 forces acting on it. Let's start with the weight of the meter stick itself. So all objects have what we call a center of mass. And the center of mass for a nice symmetrical object like a meter stick, where does the center of mass go? Directly in the middle. So the weight of the meter stick goes right there. So that's going to be mg for the meter stick. Make sure your mass is in kilograms. So you guys are all good physics students now. I mean, you've always been good physics students, but now you know. You look at this. What do we have to do to 175 grams? Put it in kilograms. Okay, so that's 0.175. 175 grams. That's the same as 0.175 kilograms. And then we multiply that by 9.8. So the weight of the meter stick, this mg, let's put the number in. When you do mg for the meter stick, it's 1.715 newtons. And don't round it because it'll cause rounding error, which becomes important, especially for a problem like number 2. Okay, so then what else do we have? We're told in the problem that we have a 50-gram mass at the 20 centimeter mark. So the 20 centimeter mark is going to be somewhere around here. And 50 grams is 0.05 kilograms. So that comes out as 0.49 newtons. Yo.
50 grams, not 20. Got it.
Yep, 50 grams. Yep. And then, so ooh, wait. Oh, dude, you know what? I messed up when I wrote this. Number 2, sorry guys. Number 2 talks about an 85-gram mass on the meter stick. I should have put the 85-gram mass up here because for number 1, number 1's calculation requires the 85-gram mass there. So we also have an 85-gram mass hanging here. So we have a third mass down, a third mg force on it, and then this comes out as 0.833 newtons. Okay? And then what's the 4th force? We have one more force. There must be a normal force holding everything up. Okay, so normal force, the axis is a little nail. So the little tiny nail that the ruler is resting on is the surface holding everything up. Okay, the first question, what's the normal force on the meter stick? And as I said, this 85-gram mass, I should have put him up here in the given.
So you just add the mg's, right?
So how are we going to solve for the normal force? To find the normal force, we look at the situation, and what has to be true? The upward normal force must be equal to the 3 down forces, right? The total up force must equal the total down force. Does that make sense?
3.038.
So you sum the forces. You go sum of the forces. We have normal force up minus 0.49 down, minus 1.715 down, minus 0.833 down. The sum of the forces always equals ma, so equals ma, but what's the acceleration of the meter stick? 0, so that equals 0. So now we can solve this for the normal force. The normal force comes out as 3.04. Just sum the forces. Easy.
You're rounding up.
I think I rounded it slightly. Okay. Now, second question. Second question is where we're going to get torque into this. Now let's review torque. Okay, to solve the second question, so we know that this 20 gram mass, or no, I'm sorry, 50 gram mass, this is the 50 gram mass. We know that he's at the 20 centimeter mark. We know that the axis is at the 50, so you got to keep track of your locations. So what's the distance from the axis from here over to there? What's that distance in here? 30 centimeters. This distance here is 30 centimeters, which is 0.3 meters. Okay, that's 0.3 meters. I just subtracted the two. The mass is at the 20 centimeter mark. The weight of the meter stick is at the 50 centimeter mark. And that's the axis. We got 30 centimeters. Okay, now what's the distance in here? From here over to this force is x. That's what we're solving for, x. Now before I do this, let's just review torque. The equation for torque is force times lever arm. R is the symbol for lever arm. Why they chose R, I really don't know. You could call it D. Some books call it D. Our textbook uses R. Torque equals F times R. R has a special name. What's the name for R? The lever arm. And the lever arm, it's where we get the word leverage from. The definition for lever arm, and if you don't have this definition written down from last week, I would write it down. Lever arm is the perpendicular distance from axis to force. Does everybody have that written down? It's the perpendicular distance from axis to force. So if you look at this situation, it's pretty nice, because here's our axis. Our axis is this point right here, the center of the meter stick. So 0.3 meters when you go from the axis over to this force, is that perpendicular? Is the 0.3 meters perpendicular to the force? It is. So that's good. Is the x perpendicular to that force? Yes. So we have our distances. They're perpendicular to the force. They're measured from the axis. When you do torque problems, you always measure from the axis. So the next thing we got to talk about is the sign convention for torque. We're almost done. The sign convention for torque, it's not going to be up, plus, down, minus. Because what's torque all about? It's all about rotation. So the sign convention for torque is going to be clockwise, counterclockwise. Okay? So what's this force here doing? Is this force here clockwise or counterclockwise? That's clockwise. This force over here, counterclockwise. So which one should be plus and which one should be minus? It doesn't matter. Let's just say clockwise is plus, counterclockwise is minus, okay? Or if you want to, you could do it the other way. You could say counterclockwise is plus and then clockwise is minus. As long as you're consistent, it's fine. Now, dudes, what about the normal force and the weight of the stick itself? The normal force and the 1.7. Are those guys causing a torque? No, because they're on the axis. If a force is on the axis, what's the distance from the axis to the force? 0. So in other words, your R is 0 for those two forces. A force on the axis causes no torque because the lever arm is 0. And look, if you don't believe me, try pushing here. If I push on that axis right there, is the meter stick going to rotate? If you push on the hinge of a door, is the door going to turn? A force on the axis causes no torque. All right, so we're ready to solve this. So let's just erase this up here. Make some room. So here's what your solution looks like. So we're going to sum the torques. How many torques do we have here? 2. We got this torque and this torque, the 2 torques. So let's start with the positive one. So we're going to go 0.833 newtons times x. So look, what did I just do there? The torque equation is what? Force times distance. And they have to be perpendicular. Is the 0.8 perpendicular to the x? Yep. Okay, then we go minus, then we go to this guy. 0.49 newtons times 0.3 meters. So those are the two torques. In this class, the torques will always cancel, meaning the object won't rotate. So the sum of the torques will be equal to 0. So now we have a nice equation where we can solve this for x. And x comes out as 0.176 meters, which is 17.6 centimeters. Is that the answer? Because what's the question? If you read the question, it says, where must the 85-gram mass be hung to balance it?
50 plus 13.
So where did we measure where is this 17 centimeters measured from? It's not from 0.
50.
It's measured from the axis, right? It's measured from the axis. So we're looking for this location right there. What's that location going to be? Well, it's going to be the 50 plus the x, so it's going to be 67.6 centimeters. If you hang the mass there, the meter stick will balance. All right, now, on to the lab. So that's the pre-lab problem. I'm going to end this video here.